weight, pressure altitude, and head or tailwind component. The base condition is for zero runway slope and ISA temperature with corrections for runway slope, temperature above ISA, speed above VREF plus 7 knots, and steep approach. Tailwind landings are prohibited on contaminated runways with a downhill slope. With a headwind, the maximum allowable downhill slope is 0.5%. We now calculate a landing distance on a wet runway at 2,000 feet pressure altitude with a tailwind of 5 knots. The aircraft weight is 37 tons and a landing distance required is 1,550 meters. For eventual slope and temperature corrections, we have to use another table. The slope is 1% downhill and the temperature is ISA plus 10. For the slope, we add 40 meters and a further 3% for the temperature. We end up at 1,638 meters required landing distance for this landing. The landing data calculation for contaminated runways is basically the same, but note that contaminated landing data has reduced safety margins of only 15%. Operations from contaminated runways should be avoided whenever possible and precautions taken. Aim to make a positive touchdown on a contaminated or low braking action runway. Use maximum braking throughout the landing roll and achieve a low forward speed before exiting. It is essential to achieve an accurate touchdown speed and aim to touchdown within the first 10% of the runway length. If the touchdown speed is likely to be fast or the touchdown point well down the runway, the approach should be discontinued. Moreover, reduced crosswind limitations should be applied, the same as for the takeoff. Note that tailwind landings are prohibited on contaminated runways with a downhill slope. With no wind or a headwind, the maximum allowed downhill slope on contaminated runways is 0.5%. There are also tables for performance-relevant system failures containing multipliers which have to be added to the scheduled flap 33 landing distance required. The resulting landing distance then has a safety factor of 67%, and if it is practicable to use this distance, we are finished. If it is not practical to use the fully factored distance, check the multiplier color code. If the color code is pale or amber, use the 33 flap landing distance required. For a pale background, a safety factor of at least 33% will be given for a wet or dry runway as appropriate. For an amber background, you have only 15% safety factor for either wet or dry runways when using the scheduled 33 flap landing distance without the multiplier. If the color code is red, multiply the 33 flap landing distance required by the multiplier from table 6.14. The landing distance obtained from the multiplication will have a safety factor of 15%. The multipliers are not intended for use with contaminated runway data. Landings on contaminated runways are prohibited with the failures in the tables. The following failures are covered: flight control system failures, hydraulic system failures including flight control failures, electrical system failures including flight control failures, brake system failures, ice protection system failures. When not using the 67% factored landing distance, aim to touchdown within the first 10% of the runway length and select lift spoilers if available as soon as possible after touchdown. If anti-skid is available, commence maximum braking effort as soon as possible after touchdown. If it is not available, exercise extreme caution in braking. Go around if touchdown is not achieved in the first 10% of runway length. Last but not least, there is a table in the FDH that gives the maximum landing weight for flap 0. The maximum weight for landing with flaps 0 is governed either by the tire limiting speed or the energy that the brakes can absorb. The table is entered with the landing pressure altitude, wind component, and air temperature. The Avro RJ is permitted to carry out steep approaches provided that the aircraft is of the approved modification standard for approach angles between 4.5 and 6 degrees. The maximum tailwind for RJ-70 and RJ-85 is 5 knots. For the RJ-100, tailwind is not permitted. Moreover, a flap 33-degree landing must be carried out and the air brake must be operative. Steep approach reduction in landing distance. If the airfield is approved for a screen height of 35 feet and a PAPI, associated or not to an ILS, is in use, the landing distance required may be reduced by the value given in Table 5.9. In all other cases, the actual landing distance required must be used. Regulated Landing Weight, RLAW, charts may be provided with the Regulated Takeoff Performance charts, which are described in the Takeoff section. These charts provide an allowable weight for a specified runway and conditions rather than the landing distance required given in the FDH. Landing performance data is published for each runway and flap setting and usually consists of 2 tables. Landing WAT climb limit data is given for a range of OATs for either air brakes open or closed. The data is for bleed off. Add 12 degrees Celsius to the actual OAT for engine anti-ice on or 10 degrees Celsius for engine air and packs on. A correction is provided in case of ice remaining on the airframe after use of airframe anti-ice. The landing weight field length limit data is given for a range of wind components for both air brakes open or closed. A wet correction value has to be applied, if stated when landing on a wet runway. For contaminated runways, there are separate charts. The calculation principles are basically the same as for the RTOW charts. The lower of the weights calculated from the WAT climb limit and field length limit must be compared with the structural limit, the maximum certified landing weight. The lowest of these 3 values is the regulated landing weight. The WAT climb limited landing weight for contaminated runways is not affected by the runway surface, and therefore the climb limited landing weight is the same as for the dry-wet runways. The calculation process of the landing field length limited weight for contaminated runways is similar to that for dry-wet runways, but air brakes must be open. No credit for drag resulting from the contaminant is applied, and so the values are constant for varying depths of contaminant. Enter the chart with the wind component and OAT and obtain the uncorrected allowable weight. Thereafter, the QNH correction. Plus, if QNH higher than 1013 hectopascal, minus if less, has to be applied to obtain the correct RLAW. The limit code informs whether structural, field length, approach climb, or landing climb is limiting. Here you see another solution for an RLAW chart. Your operator even may have own customized charts. Most airlines and operators use computerized operational flight plans, OFPs. These are generated by flight planning data which can be found in the FCOM Volume 2. The heart of each OFP is the trip time, routing, planned flight level, and the fuel calculation. If no computerized OFP is available, flight planning can be done with data provided in the FCOM Volume 2, Chapter 2, Flight Planning. The structure of this chapter is the following and contains all necessary information to plan a flight. Eight tables show maximum takeoff weight, defined by the availability of 300 or 500 feet per minute rate of climb ceilings. Information is given for high-speed and long-range climb techniques and for both maximum and normal climb ratings. Climb norm may be used until climb max is required for a higher rate of climb. We plan a high-speed climb with normal climb thrust with a minimum climb rate of 500 feet per minute. Average temperature during climb is around ISA plus 5, and a cruise pressure altitude of 31,000 feet is desired. The resulting MTOW for that climb is 38.3 tons. Fuel consumption depends on air distance rather than on ground distance. To convert an actual sector distance to an equivalent still air distance, ESAD, 4 air distance tables are provided, covering true air speeds of 300, 360, 400, and 430 knots. Alternatively, the following formula gives the air distance, assuming tailwind positive and headwind negative. We plan a cruising TAS of 430 knots and have an average tailwind of 40 knots, and the sector length is 280 nautical miles. The resulting air distance is 256 nautical miles. Tabulated sector fuel and time data is given for 3 procedures: maximum speed based on high-speed climb, cruise at VMO, MMO, or maximum cruise thrust, and high-speed descent. This procedure is intended to give minimum sector time. Intermediate, based on long-range climb, cruise at VMO or Mach 0.67, and high-speed descent. This procedure is a compromise between the high-speed and long-range procedures. Long-range, based on long-range climb, cruise at 235 knots indicated airspeed, and long-range descent. This procedure consists of practical speed schedules intended to give minimum sector fuel or close to maximum range for a given fuel. The sector fuel and timetables comprise fuel and